Hi, welcome back to my channel. My name is Gina. In this lecture, let's talk about the inverse of a square matrix. Let's first do a scalar analogy. In scalar, for example, 2, its inverse, we denote that as 2 to the power of negative 1. So we call 1 over 2 as the inverse of 2. And if the scalar is multiplied by its inverse, then we get 1. Similarly with matrices, for a square matrix of size n by n, we call that the matrix is invertible, which means it has an inverse, if there exists an n by n matrix B such that the matrix A times its inverse equals to its inverse times the matrix, and they both equal to the identity matrix, which is like the one in scalar. And we call the type of matrices that have an inverse invertible. If A has no inverse, then we call the matrix is singular. Then how can we find the inverse of a square matrix? To find the inverse, we need this theorem. The theorem says, if I start from the identity matrix, and I perform a series of elementary row operations, let's name them op1, op2, and I did k operations, op_k. And finally I get to matrix U. Then, if I start from another matrix, for example A, and I perform the same series of elementary row operations, and with this series of elementary row operations, from A, I get to matrix B. And the theorem says, we can express this matrix B as a product of the U that we obtained from above times the original matrix. So here's a summary of the theorem. If I write my matrix in this form, on the left I have matrix A, and on the right I put an identity matrix. Then if I perform a series of elementary row operations, from the identity matrix I get to matrix U. But since on the left and the right, we are using the same elementary row operations. So the result of the matrix A, after we perform the elementary row operations, we get to U times A. Then if we want to find the inverse of A, we can simply write the matrix in this form and reduce matrix A to RREF. And if the matrix is invertible, its RREF should be the identity matrix. So we have identity equals to U times A. Then if I multiply A inverse to the right on both sides, I get identity times A inverse equals U times A inverse. And by the definition, the matrix times its inverse should equals to the identity. So, the matrix U is identity times A inverse, which equals to A inverse. So if we want to find the inverse of a matrix, we write the matrix in this form. On the left, we put the matrix that we want to find the inverse with a vertical bar and an identity. Then we try to reduce the matrix A to identity. And on the right of the vertical bar, this matrix is the inverse of A. Let's look at this example. Here we have a 2 by 2 matrix, and we want to find the inverse of A. So using what we just learned, I put the matrix that I want to find the inverse of on the left, 1, 2, 3, 4. With the vertical bar, then I put an identity matrix, 1, 0, 0, 1. And the next step is try to bring the matrix A to the identity. I can replace row 2 by row 2 minus 3 times row 1. And I get 1, 2, 1, 0. Then 0 and 4 minus 6, that is negative 2. 0 minus 3, negative 3. And 1 minus 0. Then I'm going to replace row 2 by negative half of row 2. Then I get 1, 2, 1, 0. First row remains the same. Then 0, 1, 3 over 2, and negative half. In the last step, I'm going to replace row 1 by row 1 minus 2 times row 2. Then I get 1, 0. 1 minus 3, that is negative 2. And 0 plus 1, that is 1. And the second row remains the same. 0, 1, 3 over 2, and negative half. So now on the left, I get to the identity matrix, which means the matrix on the right is the inverse of A. And that is the end of the lecture. If you are interested in the complete course of my linear algebra course, I'll put the link down below. If you like my videos, please like and subscribe, and I'll see you in the next video.